Okay, welcome to my lecture series on Laplace Transform. Now on today's lecture, I'll be basically discussing on the first shifting theorem of Laplace Transform and the change of scale property of Laplace Transform. These two properties are very important as far as Laplace Transform is concerned. And after this, I'll be doing three important problems related to these two properties. Okay, so let's come to the discussion. Now we start with today's lecture with the first shifting theorem of Laplace transform. Now first I state the theorem and then we'll go to the proof of this very important theorem of Laplace transform. Now the theorem says that if Laplace transform of ft is equal to f bar s, then Laplace transform of e to the power at into ft. That means if you multiply ft with an exponential function e to the power at, it will be equal to f bar s minus a. Now as you can see, there is a shift of the origin towards the point A, and as a result the name is given shifting theorem of Laplace transform, because initially L of ft was f bar s. When you multiply ft with e to the power at and then take the Laplace transform, it will be f bar s minus a. So a shift takes place and therefore it is called the shifting theorem of Laplace transform. It's called first shifting theorem because there will be another shifting theorem known by the name second shifting theorem of Laplace transform, which I'll discuss in my later discussion. Now we come to the proof of this very important theorem. Now how do we prove it? We prove it from the basic definition of Laplace transform. Now by definition of Laplace transform, we have, so if we apply Laplace transform on e to the power at ft, so L of e to the power at ft by definition will be equal to integral 0 to infinity e to the power minus st into e to the power at into ft dt, right? So it's from definition of Laplace transform this will come. So if you apply the laws of indices, okay, then you can write e to the power minus st into e to the power at as e to the power minus s minus a into t, right, into ft dt. So this is clear, I think, because we are just applying the simple laws of indices, and we can write this as e to the power minus s minus a into t into ft dt. Now after writing that in that form, we make a substitution. What we do is that we put s minus a as equal to p, right? Now since both s and a are constants here, so p is a constant, so there is no change in the limit because we have not substituted the variable. So L of e to the power at into ft becomes integral 0 to infinity e to the power minus pt into ft dt. Okay, because in place of s minus a we have put p. Now if you look at this integral very carefully, integral 0 to infinity e to the power minus pt into ft dt, this integral is nothing but f bar p, because we know integral 0 to infinity e to the power minus st into ft dt is f bar s. So e to the, in place of s, if we have p, so it will be f bar p, and p was taken to be equal to s minus a. So therefore if we back substitute the value, then I am getting f bar s minus a. So that is the proof of this very important theorem of Laplace transform. So if we multiply ft with an exponential function e to the power at, you will see that the result will be f bar s minus a. Now similarly, we can easily show that if we multiply ft instead of by e to the power at, if you multiply by e to the power minus at, that means if you take the Laplace transform of e to the power minus at into ft, then you will get f bar s, actually s minus of minus a, which eventually will become f bar s plus a. So that result can be used in this manner also in case if you have a negative exponential function being multiplied with the function of t, right? Now let's see that if we apply this property to the elementary functions that I have taught in my previous lecture, what results we are going to get. So if we apply this to elementary functions, these are the results that we get. So the first result is that we have already told you in my previous lecture, I have proved L of t to the power n. It was what? N factorial by s to the power n plus 1. Now let's say if I multiply t to the power n by e to the power at, then I should get f bar s minus a. Since f bar s was n factorial by s to the power n plus 1, so it will be n factorial by s minus a to the power n plus 1. Similarly, if you multiply e to the power at with sin bt, So the Laplace transform of e to the power at into sin bt will be b by s minus a whole square plus b square, right? So same thing will happen if you multiply e to the power at with cos bt, because you already have found in the, that L of cos bt is s by s square plus b square. So if we multiply cos bt by e to the power at, so there will be a shift and it will come to be s minus a divided by s minus a whole square plus b square. Likewise, if you multiply the hyperbolic functions sin hyperbolic bt with e to the power at, okay, that means if you find out the Laplace transform of e to the power at into sin hyperbolic bt, that will be b by s minus a whole square minus b square. If you remember the results of L of sin hyperbolic bt, L of cos hyperbolic bt, then you will be easily able to apply this theorem in this manner and get the result out of it. And lastly, if we multiply e to the power at with cos hyperbolic bt, and we already know what is L of cos hyperbolic bt. So L of e to the power at into cos hyperbolic bt will be s minus a divided by s minus a whole square minus b square. So the results are easily applied on the elementary functions, and these are the things that we are going to get. We get more new results based on the first shifting theorem of Laplace transform. Now, having said that, now we come to another very important property of Laplace transform, which is known by the name change of scale property. As you see, the name is called change of scale property, which means the scale of the variable is changed. Now, how it is done, you see, if you look at this statement of the change of scale property, it says that if Laplace transform of ft is equal to f power s, then Laplace transform of f at, that means you are multiplying t with a. Okay, not multiplying the function with a, you are multiplying the variable t with a. So you are trying to find out Laplace transform of f at. Then in that case, the result will be 1 by a into f bar s by a. If you look carefully, if a is 1, okay, then there is no change of scale, because change of scale doesn't take place. Okay, if you divide a variable with 1, it remains as it is. So because if a is 1, you get back the definition, L of ft is equal to f bar s. So unless it's 1, L of f at will be equal to 1 by a into f bar s by a. Now let's come to the proof that why it is so. It's a very easy proof. We use from the definition, we again start from the definition of Laplace transform, left hand side. We try to represent L of f at. So we have done that. L of f at is integral 0 to infinity e to the power minus st into f at dt. Now what we do is that we make a simple substitution. We put in place of at a new variable u. So the moment we put it, we take differential on both sides, we get du equal to a dt, and thereby your dt becomes equal to du by a. Now let's find out the limits when there's no change in the limits actually, because when t is equal to 0, u is also 0, because u is equal to at, and when t is infinity, then u is also infinity. So the change of limit doesn't take place, limits remain same, change of variable takes place, and using this substitution in the previous equation 1, if we substitute it, we are going to get L of f at equal to integral 0 to infinity e to the power minus u by a into s into fu into du by a, right? Because we have made the substitution, right? Now 1 by a can be taken outside because a is a constant, so I have taken that in the very next line, and we are left with integral 0 to infinity e to the power. I'm just writing this coefficient of u in this manner. We club s by a together and put it in bracket. See, we have clubbed this here, s by a together, because both are constants. So minus s by a into u into fu du. That's what we get finally. Now what is this integral actually equal to? If you look carefully, this is nothing but f bar s by a. It's f bar s by a. So we get 1 by a into f bar s by a. So we get the proof of this result. That means if you multiply t by a and then take the Laplace transform of f at, your scale will change. Actually it will be, unless a is 1, so it's 1 by a into f bar s by a. So that's why the name given change of scale property. Very important property of Laplace transform. Please do remember these two properties, the first shifting theorem and the change of scale property is very quite often used in a number of problems of Laplace transform. Now let's come to some examples of the discussion that we have done. We have done the linearity property in my previous class, in the previous lecture. In today's lecture, we have covered the change of scale property and the first shifting theorem. Based on all these three properties so far we have done, let's do these types of problems. The first problem, very straightforward. I ask you to find the Laplace transform of sine cube 2t. Now, to find the Laplace transform of sine cube 2t, there is no standard formula. We know we can find out Laplace transform of sine multiple angles, so sine of some multiple of t or cos some multiple of t. So, but how to find sine cube 2t? Now, from trigonometry, there is a formula that is sine 6t is actually equal to 3 sine 2t minus 4 sine cube 2t. It is actually the formula sine 3 theta is equal to 3 sine theta minus 4 sine cube theta. So if you, since this angle is 2t over here, so it will be sine 2 into 3 into 2t, which is 60. So sine 60 will be represented as, in this case, 3 sine 2t minus 4 sine cube 2t. So therefore your 4 sine cube 2t becomes 3 sine 2t minus sine 60, and you just divide by 4. So ultimately you have been able to represent sine cube 2t in the form of multiple angles of sine. That is, it is coming out to be 3 by 4 sine 2t minus 1 by 4 sine 60. Once you have done with that, now you are in a position to find the Laplace transform of sine cube 2t. So if you take Laplace transform on both sides, so what we get? We get this L of sine cube 2t becomes equal to L of 3 by 4 sine 2t minus 1 by 4 sine 60. As simple as that. We take Laplace transform on both sides. Now there was a property I discussed in my first lecture. Okay, it was called linearity property. So if you are going to, now you see here in this inside this bracket here, this is a linear combination of sine 2t and sine 60. Constants are 3 by 4 and minus 1 by 4. So since it's a linear combination of these two functions, we can apply the linearity property and write like this. This property I have discussed. So it is 3 by 4 into line L of sine 2t minus 1 by 4, constant will come outside, into L of sine 60. And since L of sine 2t is a standard form, because I have done the proof of L of sine 80, okay, so it is a by s square plus a square. So in this case of L of sine 2t, it will be 2 by a square plus 2 square. Similarly, L of sine 60 will be 6 by a square plus 6 square. So we put those values over here, and then we have to make a we have to just simplify, and we will actually get a result like this: 48 by a square plus 4 into a square plus 36. So this is the way we do this problem. So in case you get a trigonometric functions like this which is not known, you have to use the formulas of trigonometry to convert this into multiple angles and then find the Laplace transform. Now let's come to the next question here. Find the Laplace transform of t e to the power minus 40 into sine 3t. Now you must be wondering that e to the power minus 40 is there, so we can apply the first shifting theorem. But how we apply? Because to apply the first shifting theorem, the rest of the function, that is leaving out the exponential part, that is t sine 3t, this Laplace transform must be known to you. Yes, you are right, actually you have to apply first shifting theorem, but before that you need to calculate and find out first what is L of t sine 3t. Unless you find that, you will not able to get the answer of this question by first shifting theorem. Now how you get L of t sine 3t? That's the main question now. Now first of all, we know L of t. L of t is known, is standard form, so it's equal to 1 by a square. Now we apply first shifting theorem on this function t in this manner. What we do is that we multiply t with e to the power 3it, where I is root over minus 1. It's an imaginary quantity, right? So we multiply t with e to the power 3it, and if I do that, and as usual by the shifting theorem, this, your right hand side will be 1 by s minus 3I whole square, because a shift will take place. And this 1 by s minus 3I whole square I represent in the form of a complex number, because it will be a complex number. It will be in the form of a plus ib. How we can do that? We can do that by multiplying the numerator and denominator by s plus 3I whole square. So I multiply the numerator by s plus 3I whole square, I multiply the denominator by s plus 3I whole square, and thereby I end up getting s square minus 9 plus 6is divided by s square plus 9 whole square. I'm talking on the right hand side, the next line. See, I have been able to represent this part in the form of a complex number where a plus ib, where a is the real part and b is the imaginary part, because that is very important. Unless you are able to represent this in that form, then you won't be able to progress with the problem. Now let's come to the left hand side. Left hand side we had e to the power 3it. Now e to the power 3it, you know, is a very well known theorem, Euler's theorem. From Euler's theorem of e to the power 3it, we can write this as cos 3t plus I sin 3t, right? So I am writing L of t to the power 3it now becomes L of t into cos 3t plus I sin 3t is equal to a complex number on the right. Now what you are required to find out from this is that you are required to find out L of t sin 3t. Now how to get L of t sin 3t? Very easy, because we have complex number on the left, we have a complex number on the right. So basically, as usual, and they are equal. So that they are equal means their imaginary parts are equal, the real parts are equal. Otherwise, how can they be equal? So what we are doing is that we are just equating the imaginary parts from both the sides. If you equate the imaginary parts from both the sides, you will be able to get the Laplace transform of t sin 3t, which is a requirement over here. So if you equate the imaginary part, in this case I'm not interested in the real part, because real part will give me L of t cos 3t, which is not required here as per the requirement of the problem. So if we equate the imaginary part, we get L of t sin 3t is equal to, if you look at it here on the right hand side, the imaginary part is 6s by s square plus 9 whole square. So I get L of t sin 3t to be equal to 6s divided by s square plus 9 whole square. So once I get L of t sin 3t, now this problem becomes very easy, because it is multiplied by e to the power some exponential function, is multiplied by e to the power minus 40. So if I now want to find out the Laplace transform of e to the power minus 40 into t sin 3t, well, L of t sin 3t is already known, then I can do it directly. How we can do it? We apply the shifting theorem, but since there's a minus over there, so it will be plus here. So it will be 6s plus 4 divided by s plus 4 whole square plus 9 whole square. And on simplification, we get this as a result. 6 into s plus 4 divided by s square plus 8s plus 25 whole square. So this is the way we have solved the problem. We have taken the help of the Euler's theorem, the famous Euler's theorem in complex analysis, to prove this particular problem. Though this problem can be done very easily with a property that I'll tell you later on while we progress with the class. Okay, now let's come to the third example. The third example is find the Laplace transform of ft as defined as ft equal to t by capital T when small t varies from 0 to capital T and is equal to 1. That means it's constant function when t is greater than capital T. So you have to find simply the Laplace transform of this function. So if you start from the definition of Laplace transform, so definition of Laplace transform says L of ft will be equal to integral 0 to infinity e to the power minus st into ft dt. Now you very well know the interval 0 to infinity as per the function definition will be broken up into two sub-intervals, that is 0 to t and t to infinity, isn't it not? Because in 0 to t the function is small t by capital T, and for t greater than t, that is from capital T to infinity, the function is a constant function which is equal to 1. So keeping that in mind and using the differential properties, we write this in that manner. So integral 0 to t e to the power minus st into small t divided by capital T dt plus integral t to infinity, capital T to infinity, e to the power minus st into 1 dt. And then we start performing integration. So if you integrate, of course, integration by parts. So e to the power minus st into t by capital T will integrate by parts. Okay, if you integrate by parts, you can take that 1 by capital T outside the integral, which we did over here. You see, 1 by t is kept outside. Small t is taken as your first function. E to the power minus st is taken as your second function. So we write t into integral e to the power minus st, which is e to the power minus st by minus s. Put the limits from 0 to capital T minus ddt of t, which is 1, into integral of e to the power minus st, which is e to the power minus st by minus s, into dt. Limits are from 0 to t. Okay, so it's plain and simple integration by parts. And on the right hand side, it's a simple, the second integral is very simple. It is e to the power minus st by minus s t to infinity. Okay. Now, if you put the limits, of capital T first, fundamental theorem being applied. So we get minus capital T by s into e to the power minus s capital T plus at the lower limit, that is at 0. Sorry, at 0 it is 0. Then for the next term is 1 by s. We integrate e to the power minus st over here. We just integrate this one, this term I'm talking of, this term. So this term, if you integrate e to the power minus st, you will get e to the power minus st by minus s from 0 to t. Okay, the integration was not done. Now we do it, and then we are left with this e to the power minus st by minus s t to infinity. So that will be assuming the fact that s is greater than 0. Assuming the fact that s is greater than, we have to assume s is greater than 0 in this case here, because if s is not greater than 0, if s is negative, then it will diverge to plus infinity. So assuming s is positive, this tends to 0 at infinity, and the lower limit, we put the value of capital T, you get e to the power minus s capital T by s with the minus sign, and the minus sign will come from the fundamental theorem. That will make it plus, so we get a plus sign over here, plus e to the power minus s st by s, right? So we simplify a bit. So we just multiply this 1 by t with each and every term, and this t cancels. You get minus e to the power minus st by s, and from here you get t s square. S square is coming because of s being multiplied. Minus is coming here. T is being multiplied with this term, so it's t s square, and we are left with e to the power minus st minus 1. Why? Because lower limit is 0, so e to the power 0 is 1, and with the leftover term e to the power minus st by capital S. Okay, which again can be further simplified. Now these two terms cancel. You see, this the third term cancels with the first term because they are of opposite sign, so they cancel each other, and you absorb this minus sign over here inside. So you are left with 1 minus e to the power minus s capital T divided by capital T s square. So this is the final answer. Always you have to bring the answer in the final form. Okay, so this is the final answer of this particular question. So with that, I come to the end of today's class. Hope you have enjoyed my lecture. In my next lecture, we'll discuss more properties and theorems of Laplace transform. Thank you very much.